Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. Actually, it's a double good stuff today. And I am very happy to have Federica Bianco with us today. Hi, Federica.
Hello, everybody. Hello. Thank you for inviting me. I'm very glad to be here.
Thank you so much about talking about the focus issue and in particular, your very lovely article. So
thank you.
Federica, where are you located at?
I'm at the University of Delaware, and so I'm in Delaware. I'm in Wilmington, Delaware. Delaware is the second smallest state in the United States. Fun fact.
But I bet it has just about the most snow as of this point. Do you have a lot of snow on the ground?
It's melting. We had a fair amount of snow, but it is melting now. So it's quite green outside. I'm looking out my window.
That's amazing. So it is January 24th, 2022. I'm in Phoenix as we do this, and we are just barely starting to warm up as we head towards spring. So it'll be really great. That is a very awesome toy doll over your left shoulder. What is that?
So that is it's a Lego robot.
Oh yeah.
I don't know if you can quite see that, but you can see the insides of it. So half of it is transparent, the outside is transparent, so you can see that it has an organic, like it has a body structure with rib cage and bones and organs inside of it. It takes quite a long time to put it together.
Wow, very cool. No wonder you kept it up there. You don't want to take it apart. Very awesome.
And you can see the face of a sloth in the back, which I bought in Costa Rica. It's a sloth plush that I bought at the sloth sanctuary in Costa Rica.
Very cool. Very nice. Federica, what do you like to do for research?
So I do a lot of things. I have a fairly interdisciplinary and multidisciplinary portfolio of research, actually, but I was trained as an astrophysicist, primarily in data-intensive survey, a large survey type of science, and primarily in the time domain. So I think a lot about time series of things that change in the sky and how can we really understand them from photometry, from large surveys, maybe large samples. That brings me to data science and machine learning, which I do a fair bit of. Here at the University of Delaware, I'm a member of the Data Science Institute, and which brings me to my multidisciplinary portfolio of things where I study things in the urban environments. For example, we study time series of city lights to understand sort of how urban environments function, the sociology, economy, ecology of cities. And then I also have other projects in ecology. We now have a large grant that is we're working on studying mining sites and mining transactions under an NSF grant.
Cool.
So yeah, I do a lot of different things, primarily time domain, and a fair fraction of that is in astronomy.
Very cool. Very nice. And that is going to bring us to the first of two things we're going to cover today. So the first one we're going to cover is this. Wherever it is, here we go. I got to get onto the right spot and stop, and we'll do this again. Sorry, everyone. You got to do this. And this is a focus issue.
All right.
Whoops. How are we doing? There we go. This is a focus issue in the supplement, and it's the Rubin LSST Survey Strategy Optimization. And I'm going to start this very lovely coverage movie while Federica takes us away. And you go.
Great. Awesome. So let's start with the title. Let's start with the word Rubin. Rubin is the Vera Rubin Observatory, which is a facility that is under construction, supported by the NSF and DOE. It's a US facility, US and Chilean facility, which will produce, we're not seeing the animation from.
Yeah, we're not. I see that. Let's try refresh.
So Vera Rubin Observatory, yes, there you go. The Vera Rubin Observatory is an observatory under construction. The facility will be in Chile. It's being built under the support of the NSF and DOE. It's a US and Chilean adventure. And it's designed to be a really ambitious, to take a really ambitious survey of the sky, of essentially all of the southern hemisphere sky for a multitude of purposes. So it's not a survey that will do, I don't know, supernova type 1a cosmology, and some science will piggyback from it. It's really a survey that is designed to answer a variety of questions in astrophysics, including studying dark energy and dark matter, studying the transient sky, which is time domain astronomy, which again is my favorite topic, studying the Milky Way through resolved stellar population, and study the solar system, building the most complete catalog of moving objects to date. And so the observatory is under construction. It's almost finished. The survey hasn't started. The primary survey that will be conducted at the observatory is the LSST, the Legacy Survey of Space and Time, which will last 10 years. And it's currently slated to start at the beginning of 2024.
Awesome.
So, like I said, there's a lot of things that go into building an observatory. You build an amazing facility, you build an incredible camera. The camera for the LSST survey is the size of a car. It's really state of the art. But then there's the question of how do you use this instrumentation to get the best science across the board?
Mm-hmm.
So that's a question of survey strategy, right? So you can take awesome images at high resolution, wide field of view, great image quality to an unprecedented depth from an optical ground-based survey. But the sequence with which you take these images, how much time you spend on each field in the sky, how do you alternate the filters, which is everything that you're seeing in these animations that are flashing in front of you. Mm-hmm. So the detailed sequence of the images that you will take may make or break a specific science topic.
Oh, sure.
And if you have multiple sciences that you're interested in, then it becomes a really difficult problem of optimization. Because what's good for one kind of science, say supernova type 1a, may prefer a very dense observation, so you can see sort of things that evolve at the rate of days, maybe even hours in the early phases. Whereas other science goals may want a regular cadence that is lower but persistent over a longer period of time, like say slower evolving phenomena like tidal disruption events. So the question is, in the mind of everybody that builds a survey, how do I optimize my survey choices? And because Rubin will provide its data to all of US scientists with no proprietary restrictions, wow, cool. It really needs to serve the entire community. And so very wisely, I think it involves the community in advocacy and in the decision process of how do we make the survey, how do we really build the survey. So this focus issue is containing a few articles. It's an open focus issue, so we'll continue to collect articles for about a year that are really the expression of the community advocating for their science and making recommendations based on their scientific expertise on how the survey should be run, but also doing that with tools that have been created by the observatory so that they can do that with the knowledge of the impact that this has on other science cases, and in a way that leads to a convergence on this decision. Very so cool. Here you see the first article, which is the one that I'm here to talk to you about, that just explains roughly what I told you until now. And you see the first 5 articles that were accepted for publication in this focus issue. I think it's really new what we did here. We created a venue for people that from the community work towards survey construction to get their work into a peer review journal, which is uncommon because a lot of time, if your articles are about survey strategy, survey design, what you would like to do with the survey, scientific journals may not be the right venue for it if they're focused on scientific discovery, because this is pre-discovery.
Right.
And so by creating this focus issue, we were giving an opportunity to the community members that are actually putting actual work in it to get the same product that they would get from any other actual work they do in research, which seems really trivial, but it is.
Seems obvious. And yeah, just a couple of days ago, we talked with Nina about her article.
That's wonderful.
We'll be having a video coming out on that. We'll put a link to that in the description below this video. Yep.
That's great. And so these are just some of the earliest articles that came out. Most of these have to do with time domain. Not all the articles in the focus issue will have to do with time domain. Some will focus on, for example, the footprint that the survey should have, or constraints on depth in particular fields, etc. So the articles that are here are advocating for time domain phenomena, or generally focusing on time domain phenomena, but it will be more diverse once the focus issue is more complete and more publications are accepted. The second article that you see here is actually by my student, Preparing to Discover Unknown with the Rubin LSST in the time domain. And there will be another article to go with it that will talk about preparing to discover unknowns in proper motion. The following article deals with rare extragalactic phenomena, blares. These are jets that come from faraway galaxies. They're potential neutrino sources. So they enter, the realm of multi-messenger astronomy, which is super intriguing and exciting. You already mentioned Nina's article. Igor Andreoni's article is about kilonovae. It talks about what is a strategy that leads to the serendipitous discovery of kilonovae. Kilonovae are the electromagnetic counterpart of phenomena that lead to gravitational wave potentially detection. So mergers of massive stars, mergers of neutron stars with black holes. The electromagnetic counterpart, so the light that we see from those phenomena, is called a kilonova. And this particular article deals with how many kilonovae do we expect to see that are not accompanied by a trigger in gravitational waves or in neutrinos, so that you serendipitously may discover in a survey like LSST based on different cadence strategies, strategic choices. And the last one also talks about short timescales. Here, short means hour-long timescales, and identified that the majority of the simulations for LSST at this time essentially did not include observations that are in the few-hour time gap, which is really critical for some time domain phenomena that are fast, but not super fast, right? So things that last of the order of a day, like think about, I know that Eric was definitely thinking about GRB afterglows when he wrote this, right? So if you get two observations that are minutes apart, those are too close to really give you enough leverage on the slope of the rise or fall of the phenomenon, because you're just too close in time. You just don't have enough separation to really identify what the trend is in brightness change. And for some phenomena, a few hours is really a good sweet spot, because you do see the change, but you still are within the night, so you're able to perhaps organize follow-up rapidly for the next day, etc. Cool. Except few hours is tricky, right? Because it becomes hard to go back to a field a few hours away and maintain efficiency in the survey. You have very significant change of air mass, so you might now collect images that are suboptimal because you want to wait 6 hours, and in 6 hours, one of the two images is going to have to be a high air mass, right?
Yes.
So,
Mm-hmm.
so this paper deals with that.
Very cool. What a lovely focus issue. And there will be others as we get on.
Indeed.
Let's go ahead and take a look at this first article, optimizing the cadence. So we'll stop this. We will come back up to the PDF and supplement series, optimization of the observing cadence for the Rubin Observatory Legacy Survey of Space and Time, a pioneering process of community-focused experimental design. Federica, take us away.
That's great, thank you. So we thought a lot about the title. I like that I was able to put the pioneering word in the title. I always wanted to have a paper that's pioneering in the title. So let me give a shout out to the many co-authors of the paper. Particularly Željko Ivezic, who was the project scientist when we wrote the paper and just became the director of construction for Rubin, and Lynn Jones, who has been writing, who has been leading the strategy optimization team and writing a lot of software that people have used and are using to provide the recommendations that they were asked to provide. And that everybody else, every single person that is in this list has actively contributed not only to the paper and the text of the paper, but throughout the process of community-driven cadence optimization. They've contributed in a variety of ways. So you see both people from the project, from Rubin, and people from the community that appear in this list that in various ways led some aspects of this work. So this is the opening paper, in the sense that it sort of sets the stage and puts the other papers in context. And I've seen other focus issues, and generally the putting in context paper was fairly short. I think this is on the long side of papers for this kind of scope. But it was important to us to provide a detailed enough account of how this process happened, because we really do think that it's unique and it's a first to involve the community to this degree in a decision about a national survey. And we thought both that it was important for historical purposes to record the process, as well as to provide information to people that may want to engage in such community-driven or in the involvement of the community in this kind of decisions.
Nice.
So I don't know, it's about 10 pages or so, and mostly it talks about really the history of this process.
Okay.
So of course, in it you can find the description of the survey, a fairly high level description of the survey, a bunch of references if you want to know more about LSST, and then it talks about the cadence and the observing strategies of LSST. So let me actually point out that some hard constraints on the strategy are set by the scientific priorities that I've outlined before. Dark energy and dark matter, the study of the galaxy, the exploration of the transient sky, and the solar system. So those four science goals were actually set kind of deliberately to push the survey into an ambitious direction, because some of them are very different. And to enable all of these four things at once, you need exquisite image quality, you need many filters, you need colors, and relatively dense time series. You need a large footprint. So it sets a lot of constraints that are hard-coded essentially in the strategy. Those constraints are the ones that you find in this document referred here as SRD, the science requirements document.
Okay.
And roughly speaking, this means that the survey will collect about 825 observations in each pointing, at each pointing. Now the pointing is nearly 10 square degrees, so an LSST pointing is a large chunk of sky already.
Yep.
that the visits will be 30 seconds in durations, and that the minimum footprint that will be covered with these over 800 observations, 30 seconds observations, is 18,000 square degrees. That's a very large fraction of the southern sky. So this is a large survey.
Over 6
and that it will do so in 6 filter, UGRIZY.
Mm-hmm.
So those are hard constraints. There are also some hard constraints on what we expect the median scene to be and things like that, or the maximum air mass, etc.
Mm-hmm.
But if you scroll down, the first figure that you see is the figure of the 18,000 square degrees of survey, right? Okay. So on the left side, you see sort of what the survey, what a very high level conceptualization of the survey is. And on the right side, you see a potential alternative survey footprint. So here the color indicates the number of visits on the survey, and you see that the majority of the sky is in this sort of 900, 800, 900 range. Those are the 825 nominal images that I mentioned before. So that chunk of the sky that is green there is labeled as WFD. That means wide, fast, deep. And it's the main survey that will accomplish the 4 goals that I mentioned earlier.
Okay. I'm with you.
That will not take the entire on-sky time of Rubin, though. There is time left over, which we expect to be somewhere between, 20% and 10% of the sky time, which, whatever, it's only 10% of the time, but we're talking about 10% of the time at an exquisite site in Chile where you get many hours of observations per night for 10 years. Every night.
It adds
up.
Adds up,
right?
Adds up.
And so that time will be split into different surveys. So you see here a few of them. NES stands for North Ecliptic Survey. Okay. SCP stands for South Celestial Pole. Mm-hmm. GP stands for Galactic Plane. Yep. So on the left is this sort of naive high-level conceptualization of how the survey might look. On the right side is already an alternative that is driven by these community contributions that advocated for example, the anti-bulge. So that's the little chunk of purple that you see on the left to be observed the same way as the galactic plane. And the other thing that you see here is the DDF. So those are deep drilling fields. Yep. There are 5 pointings that Rubin will observe. Those have been selected already some years ago. They're extragalactic pointings that coincide with well-studied areas of the sky and areas of the sky where multi-wavelength information has been collected. So there is a good overall catalog that can significantly be enhanced by these deep observations. So these will be observed to a higher depth than the regular survey, which, by the way, I forgot to mention what the depth of the survey is, right? Okay. So the nominal depth of the survey for each one of these 800 visits is about magnitude of 24 in G-band, roughly. So that's really deep for a ground-based survey. Absolutely. And once you stack up and add these 800 images into a co-added image, it will go down to magnitude about 27. Wow, cool. That is way cool. For the whole green part of the sky. So that's a lot. Yep. And even further down for the deep drilling fields. Sure. Yep. Awesome. So, right. So this histogram is showing you how things, even once you have fulfilled these requirements, these 800 images with these 30 seconds, etc., you can have a very large, very significant difference in some of the key parameters that enable certain signs and might impair others, or vice versa. Here is the median time gap between, actually, here's the distribution of time gaps between images in any filter at the top in gray, and for each individual filter going down. Okay. And so both these panels represent survey strategies that fulfill the requirements that we talked about.
Okay.
825, 30 seconds, blah, 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 but lead to a very, very different distribution of time gaps,
Yeah.
which may lead to some science being successful and others not so much. And so we want to optimize it so that we choose these internal higher level parameters, higher level choices, so that we can enable the most science. And that's the whole name of the game.
Right. Right. So at a really high level, what's the difference between baseline and rolling?
So baseline is kind of like the name. So each one of these names, you see, it's a complex name, right? Because the first part indicates a family of simulations. Oh, perhaps I could have been clear about this. So when you see one of these, it means like there was a simulation of the survey that was done for like 10 years of simulated observations.
Okay.
This is done with a software that was built a few years ago by Rubin that is called the OpSim, Operation Simulation. Essentially adds weather constraints, telescope, downtimes, all of that. And it says, okay, if I give you these directives, you, the scheduler of the survey, where are you going to observe at any point in time? And the directives might be, I want 825 images by the end of 10 years, and I want the time gaps to be no larger than 3 days or something like that.
Okay.
And the scheduler will simulate the whole survey. So now you get, as an output, you get a list of observations, a catalog of observations, from which you can extract parameters like we did here. Here we extracted the time gap between observations in each filter or in any filter. And the way you extract these parameters from the survey is another software that was also built by Rubin for the purpose of engaging the community. It's called the MAF, the Metric Analysis Framework. And it's essentially like a Python library that allows you to interact with the simulations and extract information from them.
Okay.
So back to the name. So this is baseline is a family of sort of, think about it as naive implementations of the basic requirements.
Okay.
And then all the other families are more specialized and explore some specific aspects of the survey strategy. In this case, the word rolling means, what if we didn't distribute the 800 observations across the sky over 10 years evenly? What if we were front loading some areas of the sky and then observe them less later on? And you can do that really like hard. You can say, I'm only going to observe this part of the sky is only going to observe for the first 2 years, and then this part for 2 years, and then this part for 2 years. That's not a good idea, turns out, for a lot of science that Rubin wants to do. But you can do it more gently and say this area of the sky might receive 30% more observations, and then go down to eventually at the end of the survey receive 30% fewer observations than another area of the sky.
Gotcha.
So that's the rolling family.
Yeah.
This is, if I remember correctly, the scale 0, but I might be wrong, but the scale 0.9 means this is a fairly aggressive rolling strategy.
Okay.
Some of these numbers will indicate whether you're doing a gentle rolling or hard rolling, and what's the size of the sky over which you roll and things like that. So, but they're just two examples of two families of potential strategies under consideration by Rubin.
Right. Now you can imagine you could have many different flavors of these.
And you have, so there have been hundreds of simulations made to date. At the very end of the paper, there is a very long table that lists how many simulations were made for every phase of the engagement with the community. And some of them are like 170 simulations.
Wow.
But thankfully, Rubin has built all this software that really enables automated the automated analysis of the simulations once you have figured out what is your scientific goal and how you measure its the effectiveness of the surveys with respect to that goal.
Cool. And
so this figure shows it shows one random night, sometimes in the survey. And I like it because it's so nice and colorful, but it's really.
It looks like a quilt. It looks like a quilt, you know?
Oh my God, we should definitely quilt it. I should knit a sweater out of that.
I would buy one. I would buy one.
Gadget to be made. So this is just one night. So it actually is a much simplified version of the plot as it will be made for operations to consider. So what you see is the alternation of filters indicated by the colors on the right side.
Yeah.
You see the nighttime, so the dark bands at the edges of the figure at the top represent when it's too bright to observe, and then twilight is in gray. There's the location of the moon as an orange band going across, and there are some downtimes, some telescope downtimes, might be due to weather, might be due to telescope issues that have been simulated. Those are the white gaps.
Got it. Okay.
Essentially, white gap means you're not observing. And if you look closely, you see that there are white gaps in between observations throughout. So the slightly larger one that are between different color blocks are the time that it takes to change filter. Now, keep in mind, like I told you, the camera is the size of a car. Yeah. The filter is correspondingly enormous.
Rotate.
So, but in fact, it takes only seconds to change filter for any of the filters that are mounted on the filter wheel.
Right.
In fact, at every point in time, you can only have 5 of the 6 filters mounted on the filter wheel. So to actually put the 6th filter in, that takes longer. But the internight changes are quick. And then one thing that you see here, one reason why we decided to include this figure is because you kind of see the interplay of the mechanical constraints, the alternation of the filters, these wide gaps, et cetera, with the astronomical constraints, right? So there is a reason why Y band which is purple, is in the top right block, because that is also the time where the moon is up. So it is most effective to observe with Y band compared to, say, for example, U band would not give you a good throughput. So you kind of see the interplay of technical, mechanical constraints with astronomical constraints. And you can make one of these for every single night of every single, so sorry, this is 1 month, not one night, of course, I misspoke earlier. So one row of this is 1 night. And you can make one of these for every single day of the 10-year survey. So nice. A lot of data to think about.
Definitely, because 10 years, it's 120 of these things. Yeah, quite a bit.
Yeah.
Cool.
So let me bring you to the next figure, because this addresses what is really dear to my heart, which is really the community involvement. So right now I told you what the problem was and what were the things that were done by Rubin to enable this decision with the involvement of the community.
Okay.
So the community in Rubin, as I said, the potential user pool is anybody in the US and anybody in Chile who has direct access to the data with no proprietary restrictions, and a number of international communities that have obtained access through exchange of in-kind contributions with Rubin, with NSF and DOE. Okay. So it's an enormous users community. Primarily, the community is organized, self-organized into science collaborations. There are 8 science collaborations, and the reason why I come into the picture is because I've been serving as the science collaborations coordinator, so the coordinator of the 8 science collaborations for the past almost 6 years. So the words that you see here, exactly like TVS, SSSC, stands for Transients and Variable Science Collaboration, Solar System Science Collaborations. Then you have Stars Milky Way Local Volume Science Collaboration, Strong Lensing Science Collaboration, Informatic and Statistics Science Collaboration, Galaxy Science Collaboration, the DESC Dark Energy Science Collaboration, which is the largest, and the AGN Science Collaboration. So this graph shows the number of papers that were contributed in the first call for contributions. So first call for white papers that Rubin put out. They said, we want to optimize the survey. What do you have to say about science drivers and what strategies would work for your science drivers of the strategies that we are simulating? And the majority of the people that responded were in a science collaborations. And in fact, many were in more than one science collaboration. So on the right side, you have a core diagram that indicates every one of the 40-some papers that were submitted.
Yep.
The size of the circle is the number of co-authors. So some of them were really, really large. Some of them were single author papers.
Yeah.
And the lines between the indicates the network of co-authors.
Yes.
So you can see the color is color coded by the lead author membership in a science collaboration, but you can see that there are lines that join all the colors, which means people who have worked collaboratively across science collaboration to optimize the science goals. And other or unknown, sorry.
That's okay, keep going. I'm getting there. I'm going going to the internet.
Oh yes.
If I can get there.
Right, there is an interactive. There's an interactive version of this figure where you can see the title of each paper and the co-author network for each one of the papers. And when you look at the other primarily was also people from the community that are not involved or self-identified as involved in science collaborations, but also other projects, say Roman or Euclid, that have led papers that talked about what the strategy should be to maximize synergy with the other surveys. Mm-hmm. And so, exactly. So when you look, when you scroll onto one of these bubbles, you see the name of the paper, you see the science collaboration, the number of authors, etc., etc.
Very cool.
And all these authors, all these papers have been shared and made public on a website, on the Rubin website. And this was just the first call for papers, which was from 2018. And then we had a more recent one for what we called Cadence notes, which were delivered in April, I think, if I remember correctly, of 2021. And the majority of the papers that end up in the focus issue will be essentially these Cadence notes, but they also give the people that wrote them an opportunity to talk more extensively about the work that was behind the Cadence notes. Because when you turn it in to Rubin Observatory for a decision, it better be, nice and succinct and very, very short, so that you can grab the attention of the reviewers. But when you have the ability to write a paper submitted for peer review, then you can put all the details and all the work that went into it.
Mm-hmm. I like this interactive. Very nice. Okay, let's go back to the main events.
So finally, I have one more figure that I want to talk about. Mm-hmm. So the thing is, the hard part of this process is that, okay, so now you have an idea that you want to make a survey. You have some high-level requirements for the survey. You know that you need to finalize the details, and that may have a really important impact on science. Mm-hmm. And you want the community to be involved, so you organize a mechanism for the community to tell you how their science is impacted by your decisions, potential decisions.
Right. Mm-hmm.
You had to put all these inputs together. And that is the very, very hard part of the process. Yeah. So Rubin has organized a committee, the SCOC, the Survey Cadence Optimization Committee, which includes members of the community. It was formerly led by Željko Juvezic, and I have now inherited it. So I'm the new chair of that committee. Our first full committee meeting since I started chairing it is today. So wish me luck. And the committee will look at all these contributions, review all these white papers first, and Cadence notes afterwards, and make recommendations that balance these requirements. Mm-hmm. One way in which it analyzes these requirements is this kind of plots. So this is called the radar plot. Yeah. So on a radar plot, if the community uses the MAF software, the metric analysis framework, sets a scientific goals and analyzes the options based on that scientific goal, ideally, you get a number out of it, a metric. that is, for example, 1 if the survey is excellent for that science purpose, and 0 if it really doesn't work.
Okay.
And so if this can be done, which is not strictly true for all the science cases, because in some science cases it's hard to say what is a 1 and what is a 0, right?
Right.
But assume, let's just make it simpler and say that this can be done. Then you can plot multiple metrics, and these are the different corners of these radar plots. For example, the number of galaxies may be your metric. I want to observe as many galaxies as possible. I have an ideal number of galaxies that gives me a 1, or number of stars, or fraction of near Earth objects that are of a certain magnitude.
NEOs.
And above. NEOs, exactly. Or supernova type 1a that you have observed in sufficient detail to say that it's a type 1a and actually do cosmology and put it on a Hubble diagram.
Okay.
And so this particular plot puts together some metrics that have been well vetted and are continuously being run over all the simulations. And it's showing how some of them, based on the footprint and whether or not you're rolling, so the things that we covered earlier, some of them lead to good supernova type 1a science, and some of them do not. So rolling cadences tend to be very good for supernova type 1As. Like I said, that doesn't mean that they're obviously the choice that needs to be made, because they may be bad for something else.
Yeah.
But for these metrics, everything else is more or less the same, and supernova type 1A gain from rolling. Again, just an example.
Yeah, it's one
so
example. Many of these for
right
all of your different.
And so the committee is tasked with looking at like a lot of these examples and making sense of them, and finally recommending the initial observing strategy for Rubin, which will be implemented at the beginning of the survey. The deadline for recommending it is the end of this year. Okay. So the deadline for the recommendations to be made by the Science Cadence Optimization Committee to the Rubin Operations Director, Bob Blum, is at the end of this year, which is about 1 year before the survey starts. And because you need to implement the scheduler, the strategy in the scheduler, and test it and use it in commissioning, etc.
Mm-hmm.
And also, the first year, there's going to be differences because this is a time domain survey, right? So for time domain surveys, you really need to build templates of the sky so that you can use them to compare the nightly images to. Yep. And that might mean that the first year might be a little bit different, and that's also a focus of the committee. And yeah, so the paper has detailed all this, which I told you, has reflected on the process and come up with some lessons learned.
Yes.
The one that is dearest to my heart is that we really need to figure out a way to support the community as it does this kind of work, because there is a tremendous benefit in involving the community. But the community, when it's involved as community, is not paid for doing survey optimization, which makes it difficult. And so we really need to take a look at our funding structure and how we can enable this kind of science that is pre-discovery, but that really leads to discovery.
Right. Mm-hmm.
In a way that is equitable, that allows anybody to do that, and not only people that have more means and more availability of resources. Right. And that is fair, and that impacts positively people's careers. So that's, from my perspective, of the outgoing science collaborations coordinator, that's been the first lesson learned.
Okay.
The production of software has been critical. So the OPSIM and the map that I mentioned, the documentation of that software, the transfer of knowledge for its use, those are all really critical things that we have learned how to do over time with, hits and misses. But in a process that has been extremely fulfilling. And I think it's been documented here for future surveys to be able to do that more readily and less painfully.
More smoothly.
Smoothly, yes.
Very cool. Very cool. Federica.
And
Go ahead.
anybody that wants to submit to the focus that has worked on Cadence notes, so now I'm talking to my Rubin community, people that have worked on Cadence notes, that have worked on white papers, but had not published them in 2018, the focus issue will remain open, accepting papers until the strategy is finalized by the committee. So until about the end of this year. So continue turning your Cadence notes and white papers into actual peer reviewable documents.
Yes, we will definitely take those. Very nice. Very nice. Well, Federica, I want to thank you so much for walking us through the top level of the focus issue itself, sort of putting a big bow around it, and then walking us through this sort of highlight overall process article to lead off the focus issue. So thank you very much.
Thank you for the opportunity.
Sure. And so you touched on it a little bit there toward the end, as we encourage people to continue submitting white papers on the Cadence. And where do we go with this, let's say the next 2 to 4 years, let's say?
Oh, well, the next 2 to 4 years are going to be, of course, the most exciting, because we're going to start the survey in 2024, right? So Rubin will deliver 20 terabytes of data every night, starting in 2024. And so it's going to be a transformational change in just the sheer volume of data and the modality of access, because really Rubin is going to provide the data to the open publicly. So anybody in principle can do science with this incredibly large data set.
Nice.
It's going to discover tens of thousands of transients every night. So things that change will all be flagged and provided to the community for further studies, for studies based on the survey data, for study based on follow-up. We'll put a tremendous amount of strain on our follow-up facilities, because, you know, millions of alerts every night, millions of things to potentially follow up spectroscopically. Who knows what's going to happen?
Time to get there,
but it's going to be really exciting. Right. The brokers.
I'm really looking forward to this over the next couple of years. Between this and AWST, and it's just fantastic.
Right.
Fantastic. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Thanks. Bye-bye.
Cheers. Thank you so much.
Thank you.